In this lecture, we are going to continue our discussion on how to choose ARIMA hyperparameters. This lecture will focus on the Q parameter, which is for the moving average. It's kind of interesting, although entirely inconsequential, that we are discussing these backwards in terms of the order we introduced each component of the ARIMA model. It turns out that, in the ARIMA model, it makes the most sense to discuss the autoregressive part first, then the moving average, and then the integrated part. However, in terms of hyperparameters, it's easiest to understand stationarity first, then the ACF, which is the topic of this lecture, and then the PACF, which will be the topic of the next lecture. In any case, let's continue. So this lecture is all about the ACF, which it turns out will help us determine the Q parameter in the ARIMA model. So what is the ACF? ACF stands for Autocorrelation Function. Note that this is also known as the correlogram. But before we talk about the autocorrelation function, we have to first understand what the autocorrelation is to begin with. Like the covariance and autocovariance, the autocorrelation is similarly defined. You will understand this if you didn't skip the second part of the stationarity lecture. In case you did, let's recap. As you know, the covariance is defined as this expected value between any two random variables. The autocovariance is simply the covariance between two specific random variables selected from two possibly different time points in a time series. That is, the auto part simply means that the two random variables came from the same time series. Otherwise, it is still just a covariance. Auto means self, so you can hopefully understand the semantics behind this terminology. So as mentioned, autocorrelation is similarly defined. Recall that correlation is nice because it's a scaled version of the covariance. As such, since we can always expect the correlation to be between -1 and +1, we can expect the same of the autocorrelation. Note that in some fields outside of time series analysis, such as engineering, the terms autocovariance and autocorrelation might be used interchangeably, and the scaled version would be specified as the autocorrelation coefficient. Now, these equations are nice, but how will they help us choose Q? Now that we understand what the autocorrelation is, we can discuss the autocorrelation function. Suppose that we have some time series, y1 up to y big T. If we take the correlation between each point in the time series and each point in the time series, we will get a big matrix of size big T by big T. In fact, you've already seen how we can do this. But actually, this won't even work because we don't even have multiple samples of the time series. We are only given a single time series. That is, we only have one version of y1, one version of y2, and so on. In order to take the sample autocorrelation or autocovariance, we would need multiple y1s and multiple y2s. So we can't use the typical formula for the sample autocorrelation that you saw before. In fact, it turns out that the autocorrelation function is defined as if the time series were stationary. As you recall, stationarity, either weak sense stationarity or strong sense stationarity, implies that the autocorrelation remains constant over time. Since that is the case, the autocorrelation is only a function of the distance between any two data points, y at t1 and y at t2. We'll denote this distance tau, so t1 minus t2 is equal to tau. Therefore, the autocorrelation is a function of tau, and since we assume that the autocorrelation remains constant over time, we can use all of the samples from a single time series to compute the autocorrelation for any tau. I understand that describing this in words can be confusing. However, the formula helps to provide lots of insight. The components of this formula should all seem familiar. First, we divide by t minus tau, because that's how many samples we are adding up. We divide by sigma squared, since without this, we would just have the autocovariance formula, and the autocorrelation is the autocovariance divided by the sigmas of the two random variables in consideration. But again, since we are assuming stationarity, that means that every point in the time series has the same sigma, and so that's why we divide by sigma twice. Finally, Inside the summation, we have y at t minus mu times y at t plus tau minus mu, which is exactly what goes inside the expected value for the autocorrelation. In other words, after considering every component of this equation, you should be convinced that this does in fact compute the sample autocorrelation. So what is the consequence of having an autocorrelation function, which is only a function of the lag tau? Note that we call this the lag because it's as if we are comparing two of the same time series, except that one of the time series is lagging behind by the duration tau. Well, what we get is a graph. This graph plots rho, the autocorrelation, on the vertical axis, and tau, the lag, on the horizontal axis. Usually, such a plot is called the ACF, and in some languages, such as R, this function is built right in. In Python, this function is included in statistical libraries such as SciPy and stats models. Generally, you will see a plot like the following, where the ACF at lag 0 is equal to 1, and then all the rest of the values are smaller than 1. The reason why the ACF at lag 0 is 1 is because this is just the variance divided by the variance, or sigma squared over sigma squared, which must be 1. If you want, you can check the equation for the sample autocorrelation to confirm this. The interesting part of the ACF plot is that it also plots confidence intervals. These confidence intervals can be thought of as a kind of threshold. If we see any lagged autocorrelations that are greater than the threshold, we would reject that they are equal to 0, and hence say that they are non-zero. To state it more casually, any point we find in the ACF plot that goes outside of the confidence interval, we can consider to be non-zero. Now, it's important to also remember the frequentist interpretation of confidence intervals. Since this is a 95% confidence interval, that means 5% of the time, one of the values in the ACF plot will just pop out of the confidence interval randomly. Therefore, if you have, say, 40 lags, you might expect 2 of them to just be randomly outside the confidence interval. For example, you might see one at lag 25 and one at lag 39. Usually, you can use your intuition to determine that this is happening by chance and is not actually significant. Okay, so now that we understand what the ACF plot is and how to look at one, how does this help us determine the order Q for the moving average process? Well, it turns out to have a very simple interpretation. A moving average process of order Q can be shown to have non-zero autocorrelations up to lag Q. That is, if I look at an ACF plot and I see that at lag 2, the ACF goes outside of the confidence interval, but after that it does not, then I would choose Q equals 2. Usually it will be the case that the plot goes outside the confidence interval for smaller lags as well. So as another example, if I look at an ACF plot and I see that at lag 5, the ACF plot goes outside of the confidence interval, but stays inside for values greater than 5, then I would choose Q equals 5. And the same logic applies for Q equals 3, Q equals 4, or any other Q. Now you might be wondering, why does it work this way, and how do we know that we can do this? So I'm not going to derive it right at this moment, but I may in the future for some in-depth lectures. Well, what you can do is, you can actually calculate, given a moving average process, what the theoretical autocorrelation would be. So recall that an MA1 process looks like this. It says y at time t is equal to a constant plus theta 1, a coefficient, times the previous error term, epsilon t minus 1, plus the current error term, epsilon t. In this case, we can calculate rho 1 to be theta 1 divided by 1 plus theta 1 squared. Rho 2, rho 3, and so on are all 0. If we have an MA2 process, we can do the same thing. We find some expression for rho 1 and rho 2, and we find that rho 3, rho 4, and so on are all 0. And again, these are just statistics calculations. Therefore, it is theoretically justified that for an MAQ process, all of the lags up to Q will have a non-zero autocorrelation. And that is what we are looking for when we look at an ACF plot.